Let us now talk about how vectors internally work. So we have been saying that vectors are dynamic array. Please ensure that you do not confuse with dynamically allocated array. Dynamically allocated arrays were allocated using addresses. You have something like new int, and it's a dynamically allocated array, right? The problem with this is its size is still fixed. You cannot change the size later. You have to pre-allocate space for n elements if there are going to be n elements. The dynamic array, which is vectors are dynamic arrays, where what happens, your array size increases automatically as you insert more elements. So this is a dynamic array. Arrays allocated using malloc, calloc, they are also dynamically allocated array. Vectors, they also internally use dynamically allocated array. They internally have arrays only. Vector elements are also stored at contiguous locations. So they have the advantage of cache friendliness. They have the advantage of random access. What do we mean by random access? We can access the ith element in constant time. This facility is there only with the array data structures and dynamic arrays or any kind of arrays. And vector is also an array, so they have random access. What is cache friendliness? Since the elements are stored at contiguous locations, it's very likely that there is a locality of reference and elements are there in the cache when they are accessed. So cache miss is reduced. So that's the common advantage, not specific to array, not specific to vector. These cache friendliness and random access are available in any types of arrays, whether they are dynamically allocated or they are allocated on the stack like this. They all have random access and cache friendliness. So the point here is vectors also internally use arrays, and they internally use dynamically allocated arrays, which are allocated using new malloc, which are allocated on the heap memory. Okay, what happens in vectors is your compilers, they pre-allocate the space whenever the currently allocated space becomes full. I have written a simple implementation here. The implementation may vary from compiler to compiler. So this simple implementation says that we internally use dynamically allocated array. This is fine. So this is generally with all the compilers. So if the current allocated space becomes full, you create a larger dynamically allocated array. You create a dynamically allocated array of double the size. That's the simple implementation. And then you copy the current elements to this newly allocated space. And if the copy is successful, then you delete the previously allocated space. That's the simple algorithm. This double might be something else, triple or might be something else, depending upon the implementation, but that's the basic idea. Initially, it might happen that your compilers initially allocate an array of size 0, no array, when you have created an empty vector. Or they may create an array of size 10, 20 or 1, right? Let's assume that when we create this vector, your compiler internally created an array of size 1, right? And it doubles the size every time you overflow the space. So this is what was done by your compiler, right? And you can see what your compiler does internally. How does it work internally? You have these two functions, especially this function, v.capacity, that tells you what is the current capacity of the vector. So you can do this in your compiler, you can do this exercise, create an empty vector and then call v.capacity. You will know how much memory your compiler has pre-allocated, right? So let's assume that our compiler internally allocates space for one element when we create an empty vector, pre-allocates space for one element. So 10, when you insert, you do pushback, 10 goes fine. It is inserted at this pre-allocated space. When you insert 5, this does not go fine because the vector has space only for one element and the vector has become full. Now it follows the steps that I just said. So what happens? A new space is allocated which is of double the size, so size 2. This 10 is copied here, right? And this new element 5 is inserted here. So this is a different space from this, and this space is deleted, right? Now when you insert 20, you again see that your vector is full. So what does the compiler will do? It will double the size again. It will make an array of size internally, a dynamically allocated array of size 4, and it will deallocate the space, right? So 20 goes in here. Now if you do v.size and v.capacity, if your compiler is working this way, you will get 4 as capacity and size is 3. There are 3 elements, but there's a capacity for 4 elements. It depends upon the implementation. I've considered this example, and according to this implementation, I'm saying 4, but your compiler may produce different output, and different compilers may produce different output because they might be pre-allocating some extra space according to their own strategy. But the basic thing is this: if you follow this basic idea that you initially allocate space for n elements, I have considered n as 1 here, and you do this. If the space becomes full, you double and copy. Then we can prove that the average time complexity of pushback operation is going to be big O of 1. Let us see how. How is the average time complexity big O of 1? So I'm assuming here that pre-allocated space is for n elements, and then every time space becomes full, we double the size. What do we mean by double the size? We create a dynamically allocated array of size 2n. We copy these n elements, and then we deallocate or free the memory which was allocated for first n elements. That's what we do when array becomes full first time. So what is the average time complexity for inserting n plus 1 elements? So I've considered n plus 1 because n elements will be inserted in big O of 1 time, because say n is 4. So 10, 5, 15, 20 will take big O of 1 time because you have pre-allocated array of size 4, right? So that's the time complexity for inserting n elements. When you insert n plus 1th element, a new array will be allocated of size 8. These elements will be copied one by one. Then this new element 25 will be inserted, and then this array is deallocated. So that's what happens when you insert 25. All that is going to take big O of n time, because your array is of size n. You created an array of size 2n, you copied the n elements and then inserted one more element. So it's big O of n time, right? What is the average value? If you add big O of 1 n times, what you will get? You will get big O of n plus big O of n divided by n plus 1, which is big O of n. So what do you get? You get big O of 1. 2 into big O of n is big O of 2n. You can ignore the constant, so you get big O of n divided by big O of n, which is big O of 1. So average time complexity to insert an element at the end of a vector is big O of 1, right? It's big O of 1. So vectors, they work like arrays. They allow you to have dynamic size, dynamically add elements. They have random access, they have cache friendliness, and inserting at the end is big O of 1. Although constants are slightly higher, it's not same as arrays because there is no this extra costly operation that happens suddenly. This might happen in vectors, that suddenly there is a pushback that takes a lot of time, but average time is big O of 1.